Okay, these are probably the most challenging problems. They're also the ones you need to know how to do the most because the AP people know these are the most difficult ones. They know that we are probably going to run out of time to do these. And so guarantee you're going to see a problem like this on the AP exam. So you got to master these, put the time in to make sure you understand how to do them. All right, so we have this yo-yo. And what's happening here, we're lifting our hand up so that the hand is accelerating so that when this unravels, this stays at a certain level. It doesn't go down or anything, just it looks like it's floating there, sort of. That's what it says. So force diagram, all right, well there would be a weight X right in the center and there would be a tension upward. Okay, if it doesn't look like it's going up, down, left or right or anything, if it's doing that, it must be balanced. And so whatever the weight is, the tension force must be the same amount. So got the force diagram, we figured out what the tension has to be. It has to be the same as the weight. Describe the yo-yo's motion, I'll let you do that. Find the net torque. Well, this is spinning about the center here, so that weight doesn't cause a torque. The only thing that causes a torque will be the tension. And torque is equal to the force, in this case the tension, which you should know what that is, times the distance away, which would be the radius, has to be in meters, times the sine of that angle. And we've done enough of these now, you should know what that angle is. So that would be the net torque on the yo-yo. Once you know the torque, remember torque is also equal to I alpha. So you'll know what the torque is. It tells you what I is, so you should be able to figure out the angular acceleration. Once you know the angular acceleration, remember that tangential acceleration of the hand must be equal to R alpha. And so you should be able to figure out what the tangential acceleration of the hand is. All right, the next one. This is similar, except for now, first of all, it's not yo-yo, it's a hoop now, like a bicycle tire or something. And it has this cord that's wrapped around a massless string, and it's attached to the ceiling, and we're going to let go of it, and it's going to unwind and fall down. So you're supposed to draw a force diagram, so I'll let you go ahead and do that. You should be pretty good at that now. Trying to find the tension of the string. This time the tension in the string will not be equal to the weight. It's accelerating downward, so that means the weight must be more. But it is still spinning about this spot here. So the weight does not cause a torque. Only the tension does. So they tell us it has this linear acceleration A. So that's almost like a given number. Think of it that way. So the torque is caused by the tension, which would be equal to tension times the distance away, which is R, times the sine of the angle. And you should know what that sine of the angle is because we've done that enough times. Okay. But it also says that it has this linear acceleration. So this torque is also equal to I alpha, okay? And alpha is related to A. In fact, A is equal to R alpha. And so you can make that substitution in and figure out what the tension is in terms of A. Well, if you know the linear acceleration, you should be able to figure out the angular acceleration. Okay, they're giving us now what the radius is, and they're telling us what the rotational inertia is. And so at this point, you should be able to actually calculate a number to figure out what that acceleration is downward, the downward acceleration A. You should be able to figure out what alpha is, because we know what R is. And once you know what alpha is, then you should be able to figure out what A is. Okay, so this one up here doesn't tell us the moment inertia of this, but it says it's a disk and it has a mass, it has a radius. You would not need to know this for the AP test. They would just simply tell it to you, or they'd give you an equation. It's 1/2 mr squared in this case. I know what the mass is, I know the radius, and so I can figure out what the rotational inertia of this is. So I have to draw a force diagram for this. So you should be able to draw a force diagram for that, no problem. Force diagram for that. I'm going to help you draw a force diagram for the pulley. So I'm going to call this force down over here a tension force, tension 1. This one here is not as big, tension 2. And there might be some support force up, but that's not really important because it's spinning like this. Alright, so you should be able to write a net force equation for this, a net force equation for this. I'm going to help you write a net torque equation for the pulley. And that would look like this. The net torque would be equal to the torque from T1 minus the torque from T2. And so that's going to be T1 times the radius, I'm just going to put R for now, times the sine of 90 minus T2 times the radius times the sine of 90. And that's going to be equal to I alpha. And we found I up here. And alpha would be related to the linear acceleration. And that is, if you take the linear acceleration divided by r, that would give you alpha. So I'm just going to put A over r. So now you should have 3 equations, and you should be able to, 3 equations, 3 unknowns, where you have acceleration T1, T2, and you should be able to go ahead and find the acceleration now. Okay, this last one is very similar to the previous one, except we actually know the rotational inertia of this. It says it's a frictionless surface, and so you need to draw a force diagram for this, a force diagram for this. I'm going to help you draw the force diagram for the pulley. So the pulley has a force diagram that looks like this. I'm going to call this T1, and this one here T2. T2 is bigger than T1. There might be a force this way too, but it goes through the center, so it doesn't really matter. It's spinning like this. So it gives you some stuff later on. But you can write a net torque equation similar to what you did up here. You can go torque from tension 2 minus torque from tension 1 equals the net torque, and then you could plug in for a net torque I alpha and then solve it.